Agradecemos enormemente a Nigel Peake por la excelente plática que acaba de impartir. Antes de despedirnos, permítanme invitarlos a escribir sus preguntas en la sección de comentarios del sitio de YouTube del ICAT. Ahí las revisaremos y en tiempo debido el profesor Peake. Agradecemos enormemente a Nigel Peake por la excelente plática que acaba de impartir. Antes de despedirnos, permítanme invitarlos a escribir sus... Buenas tardes. El Departamento de Óptica, Microondas y Acústica del Instituto de... Buenas tardes. El Departamento de Óptica, Microondas y Acústica del Instituto de Ciencias Aplicadas y Tecnología les da la bienvenida a la siguiente conferencia magistral. Hoy tenemos el honor de contar con la presencia de Nigel Peake de la Universidad de Cambridge, quien impartirá una plática con título The Silent Flight of the Owl. En diciembre del presente año, el Instituto de Ciencias Aplicadas y Tecnología de la Universidad Nacional Autónoma de México celebra con orgullo su 50 aniversario. El camino de este instituto ha sido largo. Inició como centro de instrumentos, continuó como centro de ciencias aplicadas y desarrollo tecnológico, hasta convertirse en el instituto que conocemos hoy en día. Nuestro instituto hoy reúne científicos y tecnólogos de diversas áreas de especialización que le permite desarrollar investigación interdisciplinaria y tecnologías dirigidas a la solución de problemas relevantes en el área de salud, de educación, medio ambiente y energía. Como parte de la conmemoración del 50 aniversario, este ciclo de conferencias magistrales busca seguir cultivando el conocimiento y las colaboraciones para el desarrollo de la ciencia, la enseñanza y la tecnología. Les invitamos a participar en las actividades programadas durante. Agradecemos enormemente a Nigel Peake. Buenas tardes. El Departamento de Óptica, Microondas y Acústica del Instituto de Ciencias Aplicadas y Tecnología les da la bienvenida a la siguiente conferencia magistral. Hoy tenemos el honor de contar con la presencia de Nigel Peake de la Universidad de Cambridge, quien impartirá una plática con título The Silent Flight of the Owl. En diciembre del presente año, el Instituto de Ciencias Aplicadas y Tecnología de la Universidad Nacional Autónoma de México celebra con orgullo su 50 aniversario. El camino de este instituto ha sido largo. Inició como centro de instrumentos, continuó como centro de ciencias aplicadas y desarrollo tecnológico, hasta convertirse en el instituto que conocemos hoy en día. Nuestro instituto hoy reúne científicos y tecnólogos de diversas áreas de especialización que le permite desarrollar investigación interdisciplinaria y tecnologías dirigidas a la solución de problemas relevantes en el área de salud, de educación, medio ambiente y energía. Como parte de la conmemoración del 50 aniversario, este ciclo de conferencias magistrales busca seguir cultivando el conocimiento y las colaboraciones para el desarrollo de la ciencia, la enseñanza y la tecnología. Les invitamos a participar en las actividades programadas durante todo el año dedicadas a esta celebración. Sin más, es un gusto para mí dar la palabra a Nigel Peake.
Well, thank you very much indeed, Pablo. And I'd like to begin by saying how grateful I am for the invitation. It's a huge honor for me for you to invite me to help celebrate your the 50th anniversary of ICAT, which I have heard much about over many years from Pablo and others, and I'm very happy and, as I said, very honored to be able to give this talk on this very happy occasion. Okay, so I'm going to share my screen, and I've got two things that I want to show you. I've got my slides, which I will show you in a moment. But the first thing I would like to do is to show you a short video, which will explain maybe what this aspect of my research is about. So let me try this. I think it's this. Okay, so this is a short film which I have taken without permission, I'm sorry, from a BBC documentary. And this BBC documentary was entitled The Superpowers of the Owl. And it turns out that owls, probably everybody here knows, are very remarkable birds indeed and have many interesting features. But the thing that I'm most interested in and I want to talk about today is why is it, or how is it, that some owls, not all owls, but some owls can fly in almost complete silence when they're hunting their prey. So let me play this video, and what you'll see is an experiment. It's a very, very poor experiment, actually, and there are going to be three different birds, and we're going to see them fly in the laboratory, and we're going to hear, or we're going to have some indication of how noisy they are. And as I said, there are some problems with this experiment, which I will indicate as we go along. I've turned the sound off. So the first bird actually is a fairly common pigeon you might find in the city, and as you'd expect, that is quite noisy. We'll see this in a moment. This bird is a peregrine falcon, which is a very remarkable bird in itself. Peregrine falcons, of course, fly very fast. And then the third bird is the barn owl, will be the remarkable thing. So we'll see the results in a minute. As you can see, all is being allowed to take off from a higher position above the microphones than the other birds, which is a bit of a fault of the experiment. Okay, so we're going to see that all again now, but this time there's going to be a trace from the microphones underneath the flight path. You can see these people watching are very excited, by the way, from what they've just seen or heard. Okay, so here's the pigeon again, and what you'll see, this is relatively noisy, very sort of broadband sort of noise all over the place. And there we go, you can see just because of the rather disordered flight of that bird as it goes over. Okay, the falcon, the peregrine falcon, it's a little different. You can see this is a very definite trace. Those traces, I think, are due to the very strong downward beats of the wing, probably from the wingtip vortex. So those are the first two birds, the pigeon and the peregrine falcon. And now for the owl. And you can almost guess what's going to happen. And the owl produces almost no detectable sound whatsoever. So let me just play that again. The owl is effectively silent to the very sensitive microphone. Well, thank you very much. Frequency, so that will be low frequency. And the other regime is going to be when the wing chord is comparable to a typical wavelength. Okay, right. So I said I wanted to justify why one should be interested in the owl, and there are two particular technological issues I want to focus on. One of them is what I've spent most of my career working on, which is aircraft noise. So out on the excuse me, in the top picture, there's the takeoff. And what you can see there on the, you look at the different components of the aircraft noise, and the different components of the engine will produce noise. And at takeoff, you can see that the jet is the biggest source of noise coming out of the back of the engine, followed by the fan, which is the rotating blade row at the front of the engine. So those are the two big sources of noise from the engine, and compared to those, the noise from the airframe, so that's due to the landing gear, due to air flowing over the flaps and over the fuselage, that is relatively small more than 10 decibels down on this decibel scale, so at takeoff. So at takeoff, you aren't really interested in airframe noise at all. However, what happens at landing is that the airframe noise becomes much more important. So the noise is still coming from the engine, mainly the fan, not so much the jet. But what you can see is that the black bar, the airframe noise, has come right up. And the reason for that, a lot of that, is due to the fact that when the aircraft comes into land, that it's deploying all these trailing edge flaps, and those are very noisy things. And the mechanism is that the turbulent flow over the wing is producing noise like a dipole, but when it gets to the trailing edge, as the turbulence passes over the trailing edge, it turns out that that is a more efficient generator of sound than just the turbulence itself, or indeed the turbulence close to the wing away from the edge. And so it's believed that a lot of this airframe noise at landing is due to the trailing edge of the wings. And so if you can come up with a solution to that, then it would be possible for aircraft to land more quietly. And that is a very big issue at places like Heathrow, where they have to have nighttime curfews on aircraft landings and takeoff because of the noise around for the people living around the airport. So one of the things I'm going to claim is that the L has solved this problem of the noise from the trailing edge of the wing. Okay. Here's another technical application which I've become more interested in recent years, and that's the noise from large onshore wind farms. So in the United Kingdom, this is not such an issue because most of our wind energy is generated by wind turbines out to sea, where the noise they produce isn't such an issue. But for onshore wind, especially close to urban centres, then the noise that the turbines produce is a problem. And in fact, for many of the very largest wind turbines, when they are close to cities, they are deliberately braked. So they deliberately run at lower than maximum power just to keep the noise down. The noise source, again, is sort of indicated on here, and it's coming from near the tip, which is the bit that's moving fastest, of course, and it's again this turbulent boundary layer moving over the trailing edge that's causing the noise. So if you can do something to solve this trailing edge noise problem, then maybe you could run your wind turbine faster, get more power out of it, and not cause any more nuisance, noise nuisance to the neighbour. Okay, so anyway, onto the silent flight of the L. So I think I've said most of this already. We're talking about owls hunting in acoustic stealth. I've already said that is important because they don't want their prey to hear them coming. It's also important because the owl is detecting the prey using its own hearing, and so it doesn't want to make noise that would block out the sound of the mouse or whatever. Okay, right. So it turns out, and this has been known for decades and decades, that owl wings have some unusual features when compared to the wings of other birds. So the first one is so-called leading edge comb. So there's a picture at the bottom here of the leading edge comb. And what it is, you can see it's a whole line of bristles or barbs in the shape of a cone. It's now, I think, understood But the role of this is the same actually as some aircraft have with vortex generators. And it's to help the owl maneuver, especially at very high angles of attack. And so, for instance, when the owl will finally swoop on its prey, it comes in at a very steep angle. And the role of the leading edge comb, we think, is to make the boundary layer fully turbulent and to stop the wings stalling. So I think this is a pretty well-known phenomenon. The leading edge comb might have some role in noise control as well, but I think it's mainly to do with the aerodynamics and allowing the bird to swoop and to take off again at very high angles of attack. Okay, so that's the leading edge comb, and I should say that many owls have that, and also other so-called raptors, so birds like eagles have that leading edge comb as well. Okay, the next feature is along the trailing edge, and remember I'm arguing that the trailing edge is very important and is very noisy. So it turns out that the trailing edge fringe is only possessed by owls which need to hunt quietly. So no other birds possess it. And moreover, there are some owls that don't have it either. So for instance, there's a family of owls, the fish owls, which hunt by catching fish in rivers. So they don't need to fly silently. So they do not have the trailing edge fringe. And there's a family of pygmy owls which feed on insects, and those don't need to be silent either, and they don't have the trailing edge fringe. So you only see this trailing edge fringe on things like the barn owl, the great grey owl, the eagle owl, owls which need to fly silently in order to catch their prey. So that's very suggestive. And what this is, this trailing edge fringe, is a series of filaments which are flexible and also very porous as well. So you can imagine it's like having the solid wing, but then on the trailing edge there's a little flappy, flexible fringe. Okay, so that's unique to owls that fly silently. And the third thing, which I think is also unique to owls which fly silently, is that the surface of the wing has got a very, very particular structure. It feels like velvet when you touch it, and when you look at it under a microscope, it has a very complicated fiber structure, and I'm going to come back to that later. And we claim that is an important feature in the sound generation as well. Okay, there's just a close-up of the trailing edge again here on the eagle owl. Okay, so what I want to do now, I'm sort of now going back to the beginning of the project. So this was joint work by myself and Justin Jaworski. And what we wanted to do was to try and understand what effect this trailing edge fringe might have. Okay. So in order to do this, we came up with a very primitive model indeed. And so what we did, we're representing the fringe of the wing on the trailing edge by a plate. And this plate is elastic, and it's also porous. So the wing is sort of going off on this picture off to the left, and we're assuming it's semi-infinite to the left. And then there's an edge, and then downstream there's nothing. So we've got it's a model of the trailing edge. And there's various conditions that have got to hold. One is, for this to be valid, one is that the porosity is very small, and that's not such a good approximation, perhaps. But also, a better approximation is that the wavelengths that are involved are bigger than the size of my holes, which is quite probably quite good. So what we have, this big equation you can see here is the equation describing the unsteady motion of an elastic plate. So if I look at some of the terms here, we've got eta sub p is the deflection of the plate, and you can recognize some maybe familiar terms there. There's the grad to the power 4 term with a b. That's the bending term in an elastic plate. There's the inertia term, m d2 by dt squared. And then there's another term on the left-hand side, the delta P, which is the pressure jump across the plate. And then on the right-hand side, there's a term there which is describing the motion of fluid through the pores and the apertures in the plate. So this is a very, very primitive, very simple model. But what we're saying is that this plate is moving up and down unsteadily due to the turbulent boundary layer on the L's wing passing over it. And the motion of the plate is being driven by the unsteady pressure distribution across the plate. But of course, that unsteady pressure distribution is being affected by the fact that the air can move through the pores of the elastic plate. And then, of course, because the plate is elastic, then we've got to take into account the elasticity of the plate as well. And so this plate model, it just applies on X negative, and then on X positive, we just have air. So in order to solve a problem like this, what you need is a so-called two-part boundary problem. And the best way to do that sort of thing is probably using the Wiener-Hopf technique. So I'm going to come back to the Wiener-Hopf technique and talk about that later in the talk. But this one is a so-called scalar Wiener-Hopf problem. Okay, so I just want to go straight to the results here. There's a great deal of analysis that you need to do to get to these results. As I said, I'll talk about that analysis a bit more for another problem. But here are some results, and this was the sort of first indications that Justin Jaworski and I had that this trailing edge problem was important. So if we just look at the graph on the left first. So if you remember, I said that the scaling with the Mach number is important. So one important scaling is Mach number to the power 8. And that's what you would have if you had turbulence and no edge there at all. The opposite extreme of that is if you have a trailing edge which is completely rigid, so hard metal, then it was shown in very, very important results by Fouts, Williams and Hall that the Mach number scaling of a rigid metal trailing edge goes like Mach number to the power 5. And that's so that's a lot more efficient, a lot louder than turbulence, Mach number to the power 8. And it's also louder than a plate without an edge, just a solid surface away from the edge, which is Mach number to the power 6. So that's why you can see on this dotted line what the Mach number to the power 5, the one with the aircraft sitting on it. So what we've plotted here, there are 4 different curves. So there's the rigid non-porous, so that's just bare ordinary metal. So that scales like Mach number to the power 5. There's then a rigid and porous, which is a solid black. There's elastic non-porous, which is blue, and then poroelastic, which is putting both together, which is the ideal situation. And so what you can see on the left-hand side, and this is why this problem is very difficult, I think, is it almost looks as if the including poroelasticity has made the noise worse. from the point of view of the Mach number scaling, because it's going like in the L range, it's going like Mach number to the power 3 or Mach number to the power 4, which is ridiculous. It's working much better at the lower frequencies, so you can see you know, that having the poroelastic thing will get you up even to Mach number to the power 7 at a low frequency. So that's an interesting thing. But the more important thing to do is not to look at the Mach number scaling, but to just look at the actual change in the sound power, because of course there's a scaling, but there's a coefficient as well. And there we start to see a more significant result. So the graph on the right-hand side is the frequency along the horizontal, and then the noise reduction compared to solid rigid metal on the vertical. And what you can see at lowish frequency, there are really spectacular decibel reductions being produced by the poroelasticity, and just by the elasticity alone as well. But for our problem, even in the important frequency range of the L, we're still getting 2 and 3 decibels reduction. So this is not the whole explanation of the problem, but it's something. And of course, from the technological point of view, these things will be significant. Okay, let me keep going. I'll miss that out. This is the first experiment that was done at Virginia Tech to test out these results. So this was in one of their wind tunnels, and they built a trailing edge, and they used different materials. So there was a rigid trailing edge, there was an elastic trailing edge, which was just this so-called mylar film, and then they made a poroelastic trailing edge by laser drilling holes in the mylar film. And here are the results that were produced. Again, sound pressure level against frequency. So what you can see, the blue one at the bottom is background noise. So that's what you would have if you had no trailing edge at all in the tunnel. The loudest curve, the rigid impermeable one, so that's the rigid bare metal trailing edge. So you can see that is up to getting on for 10 decibels louder than no trailing edge at all. And then you introduce the elastic but impermeable film, which is a little bit quieter. But then crucially, the elastic porous, the poroelastic trailing edge, which Jaworski and I modeled, you can see in this range between about 1 kilohertz and 2 kilohertz is back down to the background noise level. So in that range, the poroelastic trailing edge is effectively silent. Now you'll see straight away that at the higher frequencies, above 2 kilohertz, something has gone badly wrong, and the poroelastic material is noisier than anything else. And our excuse for that is the way that we drilled these holes, and the holes are rather rough. So we need to redo this experiment with a smoother material. Okay, so that's all about the trailing edge of the wing. I said there were 2 sort of features that were unique to the hunting owls. One was the trailing edge, the other was this rather velvety structure to the feathers on the wing surface. This is what it looks like when you look at it under a microscope. And these pictures, particularly the one on the left, made us think that this velvet material was acting a bit like a canopy. So the next experiment was therefore to take a rough surface and put a canopy above it and see what effect that had on the noise. Sorry, excuse me. So this is a sort of veil material. You can see that the surface has got these so-called embossings on it. So this is artificial roughness. And then this whole thing is put in a wind tunnel and the noise is measured. And so there are some important things going on here. So let me explain that. So let's just look at the rough wall by itself first, without any veiled thing to mimic the owl. And what you can see here, there are two measurements going on. On the left, there's the spectrum of the far-field sound, and on the right, there's the spectrum of the surface pressure that's being measured on the surface of on the rough surface itself. And what you can see, this has been done at different speeds, and the rough surface is slightly noisier than the clean surface, which is what you'd expect. Okay, so now we introduce this veil to try and mimic the effect of the owl valvers. And what you can see on the left is this far-field sound, and that hasn't changed much, except again at the very high frequencies, the veiled material is worse, it's noisier, and that's because of vortex shedding from the fibers in the veiled material. But what has changed, and this was not what we expected at all, was the graph on the right-hand side, and that's the spectrum of the surface pressure measurement. And what you can see, let's look at the slowest one here, the red curve, for example. So the solid one is the surface pressure spectrum of the rough surface without the veil. And then as soon as you introduce the veil, you get down to the dotted surface, dotted curve, which is down by almost 30 decibels, a massive, massive effect on the surface pressure. And this is not simply about blockage, because this material is very open. You can see there it's got an open area ratio of 70%. So there's something particularly significant going on here to do with the fluid mechanics. And this was very exciting to us because we do know that surface pressure fluctuations are really important for determining far-field sound. Surface pressure fluctuations that get converted into sound, if you like. So somehow, maybe if you can control the surface pressure fluctuations, as happens here on the right-hand side, then you can control the noise. Okay, so this is actually the practical device we came up with. We're putting these two things together. We're thinking about the trailing edge fringe, but we're also thinking about this veiled material, and we're saying, can we put something like that on the trailing edge of, let's say, a wind turbine blade, and will it make it a lot quieter in flight, just like for the owl? So this is what we came up with. Obviously, putting material on is not practical. So we designed these things that we called either finlets or rails. I think the finlets probably work better. And the finlets are rigid. They've been made by 3D printing, and they just sort of bolt onto the trailing edge of the airfoil. So we'll see what happens. So this is the owl-inspired device. And this then went in a big wind tunnel in Virginia Tech. It's a very, very good acoustic wind tunnel. So the walls are made of Kevlar. And the thing about Kevlar is that it contains the flow of the wind tunnel, but it allows the sound to go through. And then on the other side of Kevlar, you have very large microphone arrays, which can then do source location. So they detect where the noise was generated. And so what we have here, we've got a picture of a real wind turbine blade, a section of it, which has been mounted vertically in the tunnel. And then you can see the picture on the left, that is where we are going to put this trailing edge treatment. So the first thing is the airfoil without the owl-inspired treatment. So the flow is coming from the left, and the colors are the strengths of the acoustic sources. So this large array of microphones. There's been a lot of signal processing, and the source location has been detected. And what you can see is that the red colors, the very strongest acoustic sources, are indeed located at the trailing edge of the airfoil. So that's exactly as I said earlier, the Fowlkes-Williams effect has here been demonstrated. Okay, so that's the noisy bit, and you can see that's much louder than the background noise in the top. Okay, at one particular frequency. So what we now do is we start with that, and we now mount the owl-inspired device to finlets, and those are placed in the black box, as you can see. And you can see that apart from some edge effects, there's a very significant difference. So we've gone down almost 10 decibels again in the strength of the acoustic sources between the red parts of the trailing edge, which are untreated, and the middle of the treated region, which is where the owl-inspired device is happening. So this is at 3 kilohertz. This happens right across the frequency spectrum, and you certainly don't make things worse at low frequency. So this is a very big result, I think. The first results, this is the zero lift case, now at 3 degrees, which is a sort of design angle of attack. Then you can see that the owl device is still making things a lot quieter. And then at almost 7 degrees, where the turbine blade is about to stall, and the acoustic, the owl-inspired device is not making things worse either. Okay, and here's some flow visualizations of what's going on. And if you look at these pictures on the right here, so this is sort of downstream looking back upstream at the turbulent kinetic energy, so intensity, and which is the bit that's, if you like, producing the noise as it goes over the trailing edge. And what you can see is that the effect of putting in the owl device, the finlets, is two things. One is that the really high turbulent kinetic energy has been moved away from the wall, so that's the red bits. So if you compare the figure on the left with the one in the middle, and then if you design the fins correctly, then you can even reduce the amount of turbulent kinetic energy. And the difference between those two is that the one in the middle is a rather abrupt start, and the one on the right is more ramped, more tapered. So this is this is really really exciting results, and it's since been verified in other contexts. So what I want to do now in the last bit of my talk, and I don't want to talk for too long, and I'll stay my welcome, so I'll wrap this up quite quickly. What I want to do is talk a bit more about some mathematics, some more recent mathematics, and in particular, this mathematics is aimed at trying to explain or to model how it is that this noise reduction is happening. And there are really two things going on. One thing that's going on is what you can see in this picture here, which is the turbulence has been moved further away from the trailing edge. And the other thing that you can see here is in this picture, which is the actual flow, the boundary layer flow over the wing has been significantly changed. So the base profile, the solid blue line, is without any fins at all, and then the dotted line is with the fins present. And so what's happening is that the fins themselves are yielding significant drag to the flow just above the fins, which is slowing the flow down. So fins here are enhancing the boundary layer shear. There's much more shear on the close to the wall than before. So those are the two effects. Okay, so how do we model this? Well, what I want to do essentially is to talk about noise generation in the boundary layer. And of course, the boundary layer has got vorticity in it. And so the acoustics of vortical flow is significantly more complicated than the acoustics of, let's say, still fluid or even potential flow. So let me just describe those equations here. These are equations principally, actually, I think, due to Marvin Goldstein. But what we have is that we can introduce an effective potential. So even though the flow is vortical, you can still have an effective potential. And this effective potential can be used to give you the acoustic pressure, which is here. And this operator curly P is the third derivative. So this is quite a bit more complicated than in potential flow. And you can also use it to get V primed, which is the unsteady velocity, the acoustic velocity in the direction normal to the wall, using this operator curly V, which is set out here. So you can see the convective derivative d naught by dt is just the convective derivative depending on the boundary layer flow u. So this varies as you move across the boundary layer. And then the operator curly V, that also depends on the shear in the boundary. Okay, so we have that, and it turns out that this potential, this effective potential, satisfies this equation. It satisfies the fourth order equation. So this is quite a bit more complicated than just a simple wave equation that you would have in still fluid. With this operator D, and the operator D is actually quite a familiar thing because it's like the Rayleigh operator, but for compressible flow. So you can see that this is now a fourth order equation, but you can integrate it once to get a third order equation where this thing on the right-hand side is convected quantities. So that means the turbulence, stuff which is convected along by the flow. Okay, so we've got those, and then we've got the boundary conditions. So again, we're going to do a sort of Wiener-Hopf problem. We're going to have boundary conditions on the lower and upper surfaces of the wing, and here I'm using a slightly different sort of boundary condition. So this is easier to deal with than the poroelastic plate. So this introduces a so-called impedance, Z, and what the impedance does is that it relates the wall pressure to the wall normal velocity using this sort of operator here and that condition. So that's essentially what you have. And if you have hard walls, then the impedance Z is infinite, and then you just have zero normal velocity. So we've got those two boundary conditions on the plate. So those apply for x1 negative on either side of the plate. And then downstream in the wake, so this is for x1 positive, we have the conditions which always apply across a wake, which is the pressure and the particle displacement are continuous. So you see, again, this is a so-called two-part boundary value problem. I'm solving this third order wave equation here, but now with two sorts of boundary conditions. There's the wall conditions upstream and the wake conditions downstream. And here's a picture of what's going on. And of course, I also need to have waves radiating to infinity as well. So this is a Wiener-Hopf problem, and to do a Wiener-Hopf problem, what we do is we introduce half-range Fourier transforms. So we Fourier transform here in the x1 direction, the streamwise direction, and you split off the positive range from the negative range. And then what you do after, as a great deal of manipulation goes on, but there are quantities here which you don't know. These things are called phi1 plus or minus, phi2 plus or minus. You don't know those. And it turns out you have 4 unknowns and only 2 equations. And so you can write that as a 2x2 matrix problem. But the big problem is, as I said, 4 unknowns, 2 equations. Doesn't seem tractable. But now, thanks to the magic of the Wiener-Hop technique, you are able to solve that matrix system. And the arguments that you use are all based on analyticity. So just to give you a flavor of this, anything with a plus on it is analytic in the upper half of the K1, the complex K1 plane. Anything with a minus on it is analytic in the lower half of the complex K1 plane. And if we do a simpler case and just have rigid walls instead of the impedance conditions, then in fact this 2x2 matrix equation reduces to a scalar Wiener-Hop problem, exactly like this thing here. And so you have phi plus is analytic in the upper half, phi plus is phi minus analytic in the lower half, and this kernel K is something that you need to factorize, and this is the heart of any Wiener-Hop problem, is to factorize, to split this K into a product of functions analytic in the upper and lower half. So I'll not go into any details of that. Let me just show you some results. So the first result is showing us that the wall shear is having a big effect, but not in the direction we'd hoped, actually. So the solid line is sort of noisier. This is the sound directivity. So there's something complicated going on there. But this picture is much better. And what I'm plotting here, frequency along the horizontal axis, and then on the vertical axis is the displacement of the turbulence from the wall. And what's happening here, if we go at a particular frequency, let's say at 10 in these units, then what we do, as the turbulence moves further away from the wall, what we're doing is moving into these regions of much lower wall pressure. And remember, this was the key thing, getting the wall pressure down, which was being seen in that experiment with the veil. So there's still more work to do, but this is a sort of result confirming what we've seen in those experiments. Okay, well, I think I've talked far too much, so I've come on to my last slides. Here are some more questions. So the first question, do these finlets actually work when stuck on a real wind turbine in a field? And so that experiment is still waiting to be done. These models, as I've described, have all been done in very nice conditions, but of course, what you would have on a wind turbine is cross flow, that there would be flow along the wingspan as well as along the chord. We need to do more of this Wiener-Hop work. And there's also, I think, some related work to do in a cylindrical geometry. But I think, as I said, I've gone on far too long already. I'll stop there. And thank you very much indeed for listening. So I'll stop sharing my screen now, should I?
Agradecemos enormemente a Nigel Peake por la excelente plática que acaba de impartir. Antes de despedirnos, permítanme invitarlos a escribir sus preguntas en la sección de comentarios del sitio de YouTube del ICAT. Ahí las revisaremos y en tiempo debido el profesor Peake les dará respuesta. Muchas gracias. Agradecemos enormemente a Nigel Peake por la excelente plática que acaba de impartir. Antes de despedirnos, permítanme invitarlos a escribir